We are now into the very important bonding theory in coordination compounds. So this is called the crystal field theory. You've learned about bonding theories in your previous general chemistry class, particularly the covalent bond theory, wherein you learned that covalent bonds are formed when one atom and another atom share electrons. But such bonding theories do not fit into the they are not enough to describe or to explain the properties of coordination compounds. Hence, the chemists back then came up with the crystal field theory. And once they were able to establish this theory, they found out that this was very accurate in explaining the properties of your coordination compounds. Like I mentioned, we will discuss magnetic properties, and we will explain the colors of your coordination compounds. But before we go to the properties, we must understand first the crystal field theory. So the crystal field theory considers the bonding in a complex ion as an electrostatic interaction between the positively charged nucleus of your central metal ion and the electrons in your ligands. So recall, we defined the central metal ion as a Lewis acid. Lewis acid is an electron pair acceptor. And we defined ligands as Lewis bases. Lewis bases are electron pair donors. So this definition, the central definition of the crystal field theory, is aligned with how we defined the central metal ion as a Lewis acid and the ligands as Lewis bases. However, of course, your central metal ion is not just a positively charged nucleus. Its positively charged nucleus is surrounded by electrons. So there will be repulsive forces between the electrons of the ligands and the electrons of your central metal ion. So the crystal field theory revolves around this idea that there are repulsive forces between your central metal ion and your ligands. So in particular, it focuses on the d electrons of your central metal ion. So the electrons found in the d orbital, the outermost d orbital of your central metal ion. So since it is dealing with electrons in the d orbital, let us review the shapes of the d orbitals. So if you recall, when you studied quantum numbers back in your general chemistry in senior high school, you studied quantum numbers, right? And from there, you learned that there are 5 d orbitals in your there are 5 types of d orbitals. Okay, so you have the d subshell, and there are 5 d orbitals in your d subshell. So these are the shapes of the 5 d orbitals. So you have the so-called dz squared, wherein you have this dumbbell-shaped cloud of electrons lying along the z-axis, and this is surrounded by a donut-shaped cloud at its midpoint. So if you recall, orbitals are defined as cloud-like structures. So they are not solid spherical structures. So they are cloud-like, and they are defined as the probability of finding an electron, right? So this shape in space tells us that there is a high probability of finding an electron in this indicated space by the yellow figures. Then we have the x squared y squared d orbital, wherein we have the lobes. We can also call them lobes. Lobes of the orbital lying along the x and the y axis. And then we have the xy. The xy orbital involves lobes lying along the xy plane. So if you imagine the xy plane, so it's a plane perpendicular to your z-axis, you have the lobes of your d orbital lying in that plane, and you have the xz orbital. So the xz orbital has the lobes lying on the xz plane, and you have the yz orbital, which has lobes lying along the yz plane. So these are the shapes of your d orbitals. So in the crystal field theory, we consider the interaction of your ligands with these d orbitals. To be specific, we must define first the structure of our complex, because the structure of the complex tells us from which direction your ligands will interact with your central metal ion. So for example, this figure shows how 6 anions will interact with the central metal ion in an octahedral complex. So if you recall, the octahedral structure is the shape of a complex with a coordination number of 6. So again, the 6 anions or the 6 ligands will approach your central metal ion from the axial positions. So there are 2 axial positions and 4 equatorial positions. So this is denoted by the blue spheres here. So for each orbital, you see how the ligands will feel the repulsive forces of the electrons found in these d orbitals. For example, in the x squared y squared d orbital, we can see that there are repulsions, or there are repulsive forces experienced by the 4 ligands in the equatorial positions, because they are head-on with the lobes found along the XY axis, lying along the XY axis, right? So this means that the energy of your x squared y squared orbital will be raised, so it will have a greater energy compared to some of the other orbitals because of these repulsive forces. So if you recall, again, from your general chemistry back in senior high school, we have this concept of degeneracy of your orbitals. So again, in your d subshell, you have 5 d orbitals. Again, the z squared, xy, y squared, xy, xz, and yz orbitals. So when we say degenerate, all of the energies of these 5 d orbitals are the same. So they are found in the same energy level. But in the crystal field theory, because of the interaction of the ligands, the electrons of your ligands, some of these will have a higher energy than the rest. So their energy is increased because of the repulsive forces. Again, we've mentioned for the XYY squared, there will be repulsive forces. And if we notice, the Z squared will also experience repulsive forces. So we expect that the energy of the Z squared orbital will also be greater. So if we look at the energy levels, the degeneracy is lost. So the energies of the 5d orbitals are no longer equal. So you have the Z squared and XYY squared having a higher energy, and compared to the initial energy level, XY, XZ, and YZ will have a lower energy than the initial. So without the interaction with the ligands. Okay, so there is a lowering for the XY, XZ, and YZ, and an increase for the Z squared and X squared, Y squared. So there is a decrease for the 3 XY, XZ, and YZ because there are no repulsive forces. In fact, if you try to imagine the lobes of the XY, XZ, and YZ orbitals are not head-on with the electrons of your ligands. So they are not clashing. So there are no repulsive forces, and this actually allows for more interaction of the ligands with the positive nucleus of your central metal ion. Hence, their energy levels are lower. So from here, you see their delta knot. Okay, so this delta knot is what we call the crystal field splitting. The crystal field splitting is the energy difference of the split energy levels. Okay, so it's the energy difference between the z squared xy y squared orbitals and the xy xz and yz orbitals. This crystal field splitting is very important because it has consequence in how the electrons of your central metal ion will orient themselves once your ligands interact with the central metal ion. So what am I talking about? So let's consider chromium with an oxidation state of +2. So it has a charge of +2. And that means there are 4 electrons in its d orbital. Okay, so if you notice, its charge is +2, meaning it lost 2 electrons. So these 2 electrons came from the 4s orbital. Okay, so you have 4 electrons in the 3d orbital of chromium, or 3d subshell. So the question is, how shall we arrange the 4d electrons of chromium? Because there are 2 possible ways to arrange them. One is still following the Pauli exclusion principle, wherein you initially fill your orbitals with 1 electron, right? So 1, 2, 3. And then the question is, for the 4th electron, where should we place it? Shall we pair it with the 1st electron in this low energy orbital, or shall we place it in one of the higher energy orbitals? Okay, so again, these two arrangements are possible. So the question is, to pair or not to pair? Now remember, class, when we pair electrons, there is cost. Okay, because there is what we call pairing energy. So you have to spend energy in order to overcome the repulsion between the 2 electrons, and they become paired in the orbital. So that's your pairing energy. So now we have to ask ourselves, which is of less cost for the central metal ion? Is it the pairing energy, or is it the crystal field splitting? Now, we don't have to know the exact values of the pairing energy and the crystal field splitting. We will only do qualitative analysis for this one. Okay, so the first scenario, class, if the pairing energy is greater than your crystal field splitting. Okay, so this means that the 4th electron will prefer a position in the higher energy orbital, because the energy difference is smaller than the energy needed to pair your 4th electron with the 1st electron, right? So in this case, if the pairing energy is greater than your crystal field splitting, then you will have this electron distribution in your chromium 2 ion. On the other hand, okay, so this is what we call a high spin electron distribution or electron configuration. So if the d electrons of your chromium ion distributes themselves in this way, we describe it as high spin. It's high spin because you have a lot of spins there. You have 4 upward spinning electrons. We designate that as +1/2, right, in your quantum numbers. So it's high spin. On the other hand, if your pairing energy is less than the crystal field splitting, then it's better for the 4th electron to be paired with the 1st electron, because that will require less energy than for it to be placed in the higher energy level. So this is the case. This is how the electrons will be distributed if the pairing energy is less than the crystal field splitting. So recall, class, if two opposite spinning electrons are paired, their spins are canceled. So here we now only have two positive 1/2 spin electrons, and we describe this as a low spin configuration or a low spin distribution of electrons. Now, the question is, how can we know if it is a high spin or a low spin for a particular central metal ion? So, we will only look at the magnitude of your crystal field splitting. The pairing energy will vary from metal ion to metal ion, but we will not discuss that. So it's not included in our coverage. So we will assume that the pairing energy is constant for all metal ions. Hence, we can just look at the magnitude of your crystal field splitting. Now, the magnitude of this crystal field splitting depends on the identity of the ligand. So there are what we call weak field ligands, which give relatively low crystal field splitting. And there are strong field ligands, which cause a larger crystal field splitting in your d orbitals. And here we have what we call the spectrochemical series, and this will give you the relative magnitudes of the crystal field splitting caused by these common ligands in complex ions. So it starts with your strong field ligands, such as cyanide, nitrite, ethylene diamine, pyridine, which has almost the same magnitude as ammonia, EDTA, thiocyanate, water. This one is nitrite as well, but with oxygen as the bonding atom. Oxalate, hydroxide, fluoride. Thiocyanide again, thiocyanate, but with sulfur as the bonding atom, chloride, bromide, and iodide. So for the strong field ligands, it causes large crystal field splitting values. Therefore, it leads to a low spin configuration. Meanwhile, your weak field ligands give small crystal field splitting values. Hence, most of them will often give a high spin configuration. So remember, in this spectrochemical series, you have to be very careful for some of the ligands that can attach via multiple atoms, like nitrite. It can attach via nitrogen and via oxygen. So if it is through nitrogen, it is a strong field ligand. But if it is through oxygen, it is relatively a weak field ligand, or it's in the middle of the spectrum. So you have to memorize this spectrochemical series. So let's try with the cobalt metal ion. So we have a high spin complex because the ligand is fluoride, and we have a low spin complex, which is in which the ligands are ammonia. So again, ammonia is found on the strong field side of your spectrochemical series. Hence, it gives a large crystal field splitting value. So the electrons prefer to be paired rather than to be placed in a higher energy level. Fluoride is found on the weak field side of your spectrochemical series. So this means that some of the electrons can be placed in higher energy orbitals, or in high energy orbitals, rather than being paired in the lower energy orbitals. So again, weak field ligands would almost always lead to high spin complexes, while strong field ligands would almost always give low spin complexes. Now, that is for an octahedral structure. So of course, if you have a different structure, the splitting will be different. the splitting for for a tetrahedral complex is given here. So again, this is if we consider how the incoming ligands will interact with your d orbitals. So for the tetrahedral structure, there will be repulsion for your xy, xz, and yz d orbitals. They are head-on with the electrons of the ligands. So this is the structure of your tetrahedral. So just to give you an idea, so if you imagine a cube, the ligands are found here, 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 and here. And you have your central metal ion inside the cube. So those are the positions of your ligands. And if you imagine, they are almost head-on with your y, xz, and yz d orbitals. So these three are the ones that are placed higher than the average energy of the d orbitals, the degenerate energy. Meanwhile, the z squared and xy squared are the ones that are lower than the degenerate level. Okay, so here we see, again, there's a different splitting pattern for a tetrahedral complex. Okay, and then if we have a square planar complex, the splitting is a bit more complicated, but you just have to remember here, the x squared y squared is the one that is most repelled. Okay, so it's because they are again head-on with your ligands, and the xy as well. The xy orbital is also a bit head-on with your ligands. Okay, so there is repulsion there. And then z squared is lowered because there is no repulsion, and xz and yz as well. So this is the splitting pattern for your square planar complex. But keep in mind, class, the crystal field splitting is this one. So it's the energy difference between the two highest energy levels in your square planar complex. Okay, so for the square planar complex, if you have this crystal field splitting value, the actual delta, which is the difference between the highest and the lowest, is 1.74 of the crystal field splitting value. Okay, so you have to memorize the splitting pattern for your octahedral, tetrahedral, and square planar. I think the square planar will be the most challenging because for the octahedral and tetrahedral, they are just inverse of each other. Okay. Now that we know or we have discussed the crystal field theory, we will now connect this idea with the properties of our coordination compounds. So first, we will go to magnetic properties. So there are three types of magnetic materials or substances. We have the paramagnetic, diamagnetic, and ferromagnetic. So we can classify a material as paramagnetic if it has a small positive susceptibility to magnetic fields. It means that they are slightly attracted by a magnetic field, and this is because they have some unpaired electrons. However, these paramagnetic materials lose their magnetic property once they are exposed to an external magnetic field. Next, we have the diamagnetic. For the diamagnetic, they have a negative susceptibility to magnetic fields. So they are slightly repelled by a magnetic field. It means that all of their electrons are paired. Just like your paramagnetic, for the diamagnetic, this behavior of being slightly repelled disappears once you expose these materials to an external magnetic field. This is different from what we call ferromagnetic materials because these materials retain their magnetic properties even after you remove the external magnetic field. So examples of these are iron, nickel, and cobalt. So iron remains magnetic um, even after exposing it to an external magnetic field. It's because the alignment of the electrons remain the same. They still have the north pole and the south pole of their magnetic field. That is different from paramagnetic and diamagnetic, okay? But for this discussion, we will focus on the paramagnetic and the diamagnetic properties because if you notice from the definition, for paramagnetic, it needs to have unpaired electrons. For the diamagnetic, all electrons must be paired. And if you are guessing, that can be connected to the crystal field theory, to how the electrons of your central metal ion distribute themselves in the D orbitals. Okay. So one way, this is a very old way of telling whether a material is paramagnetic or diamagnetic. So you have this scale and you have your sample on one end of the scale balanced with weights on the other. And you have magnet here. So once you turn on your magnet, if this material is paramagnetic, it must be pulled into the magnetic field because it is attracted to the magnetic field. So the leveled scale will now be off balanced, wherein your material looks heavier than the weights on the other end of your scale. Now, if your material is diamagnetic, then it will be repelled by the magnetic field. So what will happen is that the weights will now seem to be heavier than your sample. Okay, so let's try answering this and then conclude whether the given complex is paramagnetic or diamagnetic. Okay, so how many unpaired electrons would you expect to find in the octahedral complex hexacyanoferrate 3? Hexacyanoferrate 3. The first thing we have to know is the number of electrons in the d orbitals of iron 3. So if you look at the electron configuration of iron, so for its shortened electron configuration, so you have, we can write argon, okay? For this is the shortcut. We write the symbol of the nearest noble gas. So that's argon 4s2 3d6. Now, since this is iron 3, it means it lost 3 electrons. And that makes its electron configuration. So that's argon 3d5. So there are 5 electrons in the d orbitals of iron 3. So it's indicated there, it's octahedral, which means you have the xy, xz, and yz orbitals, and you have the z squared and the x squared, y squared orbitals in a higher position relative to these 3. Now, the next question we need to answer is if cyanide is a strong field ligand or a weak field ligand. If you recall, it is actually the first in our spectrochemical series, which means that it is a strong field ligand. Therefore, it will create a low spin complex. So how should we distribute our electrons? That's 1, 2, 3, 4, 5. So again, this is your crystal field splitting, which is greater than pairing energy of your electrons. Now, because of this, it means that we have one unpaired electron. Therefore, we can say that this hexacyanoferrate complex is a paramagnetic complex. So it will be slightly attracted by a magnetic field. Next, so the complex ion, this is tetracyanonickelate 2, is diamagnetic. Use ideas from the crystal field theory to speculate on its probable structure. Okay, so we have two options here. Is it square planar or tetrahedral? So we can try with the tetrahedral first. Again, the first thing we have to take note of is the electron configuration of the central metal ion. That's nickel 2. So nickel 2 will be 3d8. Okay, so that's 3d8. So that's argon 3d8. So there are 8 electrons in its d orbitals. So if we look at the tetrahedral, again, it's just opposite of your octahedral. So we have XY, XZ, and YZ. Doesn't matter which you write first because they are of equal energies. And you have the Z squared and the X squared, Y squared. Again, cyanide is a strong field ligand. So how should we fill the electrons? We start by filling these two lower energy orbitals. So that would be 1, 2, 3, 4. And then that's the time we move to the next level, 5, 6, 7, 8. So here we see that we have 2 unpaired electrons, which means it cannot be tetrahedral because it says the complex ion is diamagnetic. For this arrangement, it should have been paramagnetic. So now let's try proving that it is a square planar. Okay, so let's look at the splitting pattern of your square planar first. So that's x squared, y squared, xy, dz squared, and then xz, yz. So remember, class, this is our crystal field splitting, which means we can distribute the electrons here in the z squared, xz, and yz as if they are degenerate. So what do I mean by that? So let's draw it. So we have, this is x squared, y squared, followed by xy. Then you have z squared, and then xz and yz. Okay. So for the first electrons, again, this is your crystal field splitting. So this is where we have that large energy gap. But for these three, we can say that the energy gap is smaller than the pairing energy. So what we have here is 1, 2, 3, 4, 5, 6, and then sorry, that includes xy as well. So that should have been so that's 1, 2, 3, 4. Now we cannot place the 5th electron here because of the crystal field splitting. So we go back here, 5, 6, 7, 8. And this explains the diamagnetic property of this tetracyanonickelate 2 ion. So our conclusion is its structure is square planar. Okay, now there is one phenomenon, class, and this is just an idea. So you just have to recognize that there's a phenomenon we call spin crossover. So this is when the pairing energy is almost equal to your crystal field splitting. So for this one, changes in pressure and temperature can cause the complex to change from a high spin to a low spin. This is for the same ligand. For the same ligand, okay, for one particular ligand and your central metal ion, the pairing energy is comparable to the crystal field splitting. So there are conditions in which you will find it as a high spin complex, and there are conditions at which you will find it as a low spin complex. So this is what we call spin crossover. So one example is this complex shown here. That's tris 2 picoylamine iron 2 ion. It's not an ion. No, it's an ion. Okay, it's an ion with a charge of positive 2. And this 2 picoylamine is a bidentate ligand, and there are 3 of this attached to the iron 2 central metal ion. Okay, now we go to colors. Okay. But before we connect it to the colors of your complexes, I would like to introduce or to probably review you of 2 types of color mixing. Okay, so we have what we call the additive color mixing and the subtractive color mixing. The additive color mixing takes place with light. Okay, so this is, if you see here in this figure on the left, those are light beams. And in additive mixing, you have primary colors, which are red, green, and blue, or RGB. Okay, these are the primary colors. So if you mix them like red and blue, you get magenta, red and green, you get yellow, and blue and green, you get cyan. And if you mix all of the 3 primary colors, you get white light. Now, you know the concept of complementary color, right? So in additive color mixing, red is the complementary of cyan, magenta is the complementary of green, and so on. Now, there is what we call subtractive color mixing. So here, what happens is that the origin of your light is white light. Okay, so you have white light as the origin, and then in your material, there is a particular substance that will remove, quote unquote, remove some components of your white light. So we are familiar with white light, white light being composed of several colors, right? You are familiar with that experiment wherein you have white light and then you pass it through a prism, you get the rainbow colors, right? So in subtractive color mixing, you just imagine, so you have white light. As it passes through a particular substance, this substance can, quote unquote, remove some of the colors in your white light, which means after passing through this substance, you will see not white light, but a particular color. Okay, so here, our primary colors will be cyan, magenta, and yellow. So if you mix, so this means if the material removes yellow, you will see color blue, right? If your material removes red, you will see cyan. If your material removes green, you will see magenta, or vice versa. If your material removes blue, you will see yellow. If your material removes all of the colors, then you will see black, because there is no more white light passing through the material. That is what we call subtractive color mixing. What I often use as an example is this question: why are leaves green? So leaves are green because there is a certain compound in there, inside of them, that removes magenta. And that's why we see them as color green. So leaves are exposed to sunlight, right? And sunlight is a source of white light. So this white light will pass through your leaves. The compounds inside the leaves will remove the magenta. Hence, it appears green to our eyes. That's your subtractive color mixing. Okay, so for example, my blouse, it's color blue because the dye used in my blouse removes color red. Removes color yellow. That's why I see it as blue. That's subtractive color mixing, and this is our basis for explaining the colors of our complexes. Okay, it's subtractive color mixing, not additive color mixing, because we are not combining light beams. Rather, we have white light as the source of our light interacting or passing through a solution of our complex. Okay. But first, class, we have to be aware, we have to recognize that there are some complexes that might not have any color. So in particular, ions, metal ions having noble gas electron configuration, or an outer shell of 18 electrons, or having 18 electrons in the n-1 shell and 2 electrons in the n or outermost shell, do not have electron transitions in the energy range corresponding to visible light. What does this have to do with electron transitions? Okay, let me so we've learned about subtractive color mixing, right? And I described it as some compound removing parts of your white light. So what is actually happening, class? Okay, and what is happening is that if you have white light, so you have white light, and this passes through, let's say, a solution of your complex ion. So of course, you have energy levels, right? In particular, like what we learned from the crystal field theory, you have your D orbitals. So for example, in the octahedral structure, so you have this splitting pattern of your D orbitals. Now, it's possible that once you expose this metal ion to white light, it can cause the electron to jump to a higher energy level. So this jump to a higher energy level, or what we call excited state, the question is, why is this happening? It's because of the white light, okay? So what happens here is that the electron absorbs a certain wavelength of light. So recall, class, light is associated with properties such as wavelength and frequency. Okay? So this electron absorbs light of a certain wavelength. Okay? That wavelength of light corresponds to the energy gap here, which is our crystal field splitting. So if the electron gets to absorb the exact amount of energy, it cannot be lower, it cannot be higher. It has to absorb the exact energy it needs to jump to this higher energy level. If it gets to do that, then it removes that particular portion of your white light. Okay? So your white light, class, is composed of these colors. Each color is associated with a specific wavelength. For example, you have the yellow part of your color spectrum, or visible light or white light spectrum. This is from 565 to 590 nanometers. So if we look back to my diagram a while ago, So you have the electrons here, and one of the electrons jump to the higher energy d orbital. So let's say this energy gap corresponds to 570 nanometers of energy. That means this electron absorbed yellow, the yellow portion of your white light. So again, if it absorbs yellow, then the color that we will see will be blue. Kasi tinanggal na niya yung yellow portion ng white light. So ang natatransmit na lang sa eyes natin ay yung complementary, which is blue. So we will see a solution of this metal ion as blue. So that's the concept class. But again, however, if you have one of these conditions, so if you have ions with a noble gas configuration, such as aluminum 3, an ion with an outer shell of 18 electrons, that is zinc. So zinc here, the outer shell is the shell 3, and you have 18 electrons. So 2 from the S subshell, 6 from the P subshell, and 10 from the D subshell. That's a total of 18. Or if you have 18 electrons in the N-1 shell and 2 in the N or outermost shell, that is exemplified by bismuth 3. So you have 2 electrons in the outermost shell, which is shell 6. And you have 18 electrons in its shell 5. Puno yung shell 5 niya. So you have 2 electrons from 5s, 6 electrons from 5p, and 10 electrons from 5d. Okay? If you satisfy these conditions, then because of the pairing, okay, there's no more room for an electron to jump to. Lahat sila naka-pair na. There's no vacant space there. There's no electron transition taking place in these types of ions. So, since walang electron transitions, walang nagiging excited state, then the solutions of these ions and their complexes are colorless. So again, class, we are not interested with the colorless solutions. We are interested with the colored solutions of our complexes. So again, class, if you already get the gist of this, if your solution absorbs, let's say, 570 nanometers, that's in the yellow region, so it absorbs yellow color, that means we will see its solution as color blue. It's always the complementary. On the other hand, if it absorbs in the blue region, let's say 460 nanometers, it absorbs blue, then we will see solution as color yellow. Okay? Again, it's always the complementary that is transmitted to our eyes. So the species in your solution, the ions there will absorb light that will not be transmitted to our eyes. So ang natatransmit sa eyes natin, yung color na hindi niya ina-absorb. Okay? So again, since it has something to do with, sorry class, let me just point this out. Again class, it depends on the ligands. Kasi nga, meron siyang kinalaman sa crystal field theory. Okay, let's consider this. So these are 2 complexes of copper. That's copper 2 and that's copper 2. So in the first complex, the ligand is water. In the second complex, the ligand is chloride. Okay, so that is tetra aqua copper 2 because it's a cation. This is hexachlorocuprate 2 because this is an anion. Okay, so if you recall in our spectrochemical series, water is higher in the series. So chloride is on the weak field end. Water is in the middle. And these two are square planar complexes. Okay, they are square planar, which means this is the splitting pattern. That's z squared and x squared y squared. Okay, so both of them are tetrahedral. So let me just draw two energy level sets. Okay, so copper 2, how many electrons are there in copper 2? We have 9. Okay, 9 electrons. But if you recall, class, okay, if you recall, water and chloride are relatively in the lower or in the weak field end of our spectrochemical series, which means they produce high spin complexes. That means they have the same electron distribution. So, pag high spin, we can distribute them on all on all orbitals first before pairing. So they have the same electron distribution. However, since water will have a larger crystal field splitting, so for water, its crystal field splitting is greater than for chloride. Okay? This means this energy gap is greater. So this is for the tetra aqua complex. And this is for the tetrachloro. Okay? This has a larger energy gap. Okay? So how can we explain why tetra aqua copper 2 is color blue while tetrachloro cuprate 2 is color yellow? So class, in our rainbow spectrum, okay, starting from the red, if you notice here, red in this region has the longest wavelength. So that's up to 740 nanometers. Meanwhile, from the blue region here, we start with 380 nanometers. Okay, so this is what you should remember. Okay, blue, short wavelength, higher energy. So wavelength is inversely proportional to energy. Short wavelength, higher energy. Now for red, okay, for red, we have long wavelengths. So if the wavelength is long, it means you have lower energy, which means of these two, which should absorb higher energy? Which should absorb higher energy? It should be water, right? It should be water. So that means it should absorb in the blue region and it should be yellow. But for the chloro, since it has lower energy gap, then it must absorb longer wavelength, right? Because it has a smaller crystal field splitting. However, as we observe here, that is contrary to what is observed. So probably, is it? Okay. This is tetrahedral. I drew the tetrahedral, yeah, this is tetrahedral. It's square planar. It should be square planar. So let me do that again. Okay, square planar. So that's x squared, y squared, xy, z squared, and then xzyz. Okay, so what we have here, 1, 2, 3, 4, 5, 6, 7, 8, 9. But again, so they have the same electron distribution. So why is this contrary to what I just discussed? A solution containing tetra aqua copper 2 absorbs most strongly in the yellow region of the spectrum. The wavelength components of the light transmitted combine to produce the color blue. Okay. Meanwhile, for tetrachlorocuprate 2, this species absorbs strongly in the blue region of the spectrum. The transmitted light is yellow. That is the observation, which means the crystal field splitting for these two complexes is not aligned with what we just learned, right? So for tetrachlorocuprate 2, it absorbs in the blue, hence it's yellow. So it means there's a higher crystal field splitting in this complex than for water. So it's an exception to the spectrochemical series. Okay, so remember, class, for the spectrochemical series, we are only considering the ligands. Okay, just keep in mind, just have an open mind that your crystal field splitting is also affected by the identity of your central metal ion. But again, for Chem 18, we are basing our discussion only on the spectrochemical series, which is based on ligands. Okay? Okay. So this is an exception. Okay. So here is another example, class. These are chromium complexes. So if you see here, if you change the ligands, so notice consistently you have 5 ammonia ligands, which and one of the ligands is just being replaced. We have chloride, bromide, iodide, nitrite, sulfate, and carbonate. You're just changing one of the ligands. But if you notice, it's changing color. Very interesting. So just a fun fact, class, your makeup, for example, most of them are colored, right? Like your eyeshadow or your blush powder. Most of these are made from metals, minerals, they would say, but technically they are metal ions and they are complexed with certain ligands to create these beautiful colors. Okay? So for this one, just appreciate the fact that just by changing one ligand, you can change the color of your complex. Okay. So here we apply, class, what we have learned from the crystal field theory. So in the previous table, it indicates that the color of hexa, aqua, chromium 3 chloride is violet, while that of hexaamine chromium 3 chloride is yellow. Explain this difference in color. So from our spectrochemical series, ammonia is higher than water. So ammonia is relatively a strong field ligand compared to water. Now this is an octahedral structure. The coordination number is 6. So we have this splitting pattern. For chromium 3, there are 3 electrons in the D orbital. So you have 3 electrons there. Now we are left to ask ourselves, which of the 2 complexes will absorb which wavelength of light? Okay, so let's look here. If it's violet, then it's absorbing green, as indicated in this color wheel. And if it's yellow, it's absorbing in the blue region. Okay. If it's purple, if it's absorbing in the green region. If it's violet, it's absorbing in the green region. If it's yellow, it's absorbing in the blue region. Okay, now let's associate. Blue has shorter wavelength than green, which means this is associated with higher energy gap. Okay. The green is associated with a smaller energy gap. That means for hexa-aqua chromium 3 chloride, it absorbs from 530 to 565 nanometers of light. And hexaamine chromium 3 chloride absorbs in the 450 to 485 nanometer region of white light. And that is aligned with our spectrochemical series. Ammonia, being a strong field ligand, has a higher crystal field splitting than water, which means for this complex containing ammonia as the ligands, it needs to absorb light with a higher energy. So it absorbs light with a smaller wavelength. Water, on the other hand, is in the middle of our spectrum, so it's closer to the weak field side, which means its crystal field splitting is smaller than that created by ammonia. Hence, it will absorb in the region with a longer wavelength. So it absorbs in the green region, hence its color is violet. Gets? So that's how we explain the colors of our complexes based on the crystal field theory. So we are using the crystal field splitting, the splitting patterns. We are using the spectrochemical series, and we are using the concept of subtractive color mixing. Okay, those three: the splitting pattern, the spectrochemical series, and subtractive color mixing to explain the colors of our complexes. And that's the end of coordination compounds. So in our next meeting, we will just practice answering countless questions, items as a review for your exam.